Hello, my name is Noson Yanofsky. We're teaching theoretical computer science. We're up to chapter 3 of Professor Sipser's book, and I'd like to review what we did. Okay, so from the beginning of the chapter, from the beginning of the book. So we're talking about formal language theory. We talked about regular languages. Then we talked about context-free languages. We talked about regular languages. Then we saw that there are certain things that can't be done by regular languages. So we got up to context-free languages. And then we found that there were certain things at the end of last class we talked about. There are certain things that even a context-free language can't do. Okay, so what's higher? Okay, and the answer is the one thing higher here is context-sensitive languages. Okay, and then there's one higher level, and we'll talk about what's the higher level in a second. But I'd like to just show you what context-sensitive languages are, and I'll explain to you the name context-free and context-sensitive. Okay, now I just want to talk about the rules for the grammars that describe these. So for regular languages, I think we call these linear. The rules have to be of this type. A variable turns into a terminal or a variable. A variable is a terminal followed by a variable. Or you could have the empty word, okay, or something like that, or just a terminal. But, right, so a variable going to a terminal and a variable, or a variable turning into just a terminal, or the empty word, okay? Context-free was a lot better, and this was more what we were dealing with for the past 2 weeks, 3 weeks, whatever, a variable, a single variable, and it goes into a whole bunch of things. Terminals, variables, a whole word of these things. Those are the types of rules. Now let me just show you what context-sensitive these rules are. So these are we're going to need a more powerful class of languages, and that more powerful class of languages is going to have allow more types of rules to be generated. Okay, and so the things will be, let me just give you an example, then I'll be a little bit more formal. You might have something like this. C, letter T, letter B, small b, capital T, small s, no, not that we don't use s, small j, okay, that goes and becomes, let's say, the letter K, the letter capital B, small capital C, small a, letter S, letter C, letter F, okay, something like that. Okay, this is a typical example of of a rule for context-sensitive languages. Now, you don't just have one letter, one variable changing into many things. You could have a whole word of things, okay, changing into a whole word of things. And this is the word where the phrase context-free and context-sensitive. Context-free means, look, I change this A into whatever word there is over here. I don't care about what A is surrounded by. I don't care what's before A. I don't care what's after A. So I am free of context. I'm not looking at where the context of the A is. As opposed to that, context-sensitive, I'm not changing just one variable into a whole thing. I'm changing a whole bunch of things into another thing. Okay? Now, that's an example. This is an example. The form is as follows. The form is you have, don't move. Alpha changes into beta. Okay, that's the rule, where alpha and beta are just like this. They're words made out of terminals and variables. So they're words made out of terminals and variables. But we have one thing, and this is why they're called context-sensitive grammars, or sometimes they're called restricted grammars. Okay? It has one rule, and the rule is the length of alpha is less than or equal to the length of beta. Okay? This guy is smaller than this guy. This has 1, 2, 3, 4, 5. This has 1, 2, 3, 4, 5, 6, 7. So it's smaller. I'm not sure about the equal sign. Yeah, it is equal. Okay, great. Okay, so these are called rules of this type. Rules of this type are called context-sensitive rules, or context-sensitive grammars, or restrictive grammars. Okay. Now we have the highest, and by the way, I am not doing anything that's not on your chart that I gave you the first day of class. Let me just get that chart. The first day of class I gave you this chart and I said regular, and we spent a lot of time doing regular, context free, and we spent a lot of time doing this, context sensitive. We are not going to spend a lot of time doing this. We're going to spend a half hour on this. Okay, and just look what it says. Context sensitive grammar is alpha to alpha prime. I wrote alpha to beta, that's fine. Alpha and alpha prime in variables plus terminal star, variables and terminals, okay, such that alpha is less than or equal to alpha prime. That's great. Okay, and finally, the highest language that we're going to deal with is RE languages. I'll tell you what that means when we deal with it. Okay, and the type of grammars that they correspond to is unrestricted grammars. Okay, and let me just tell you what those are. You have the following. Alpha goes to beta. Alpha comma beta are a member of exactly what I wrote here, sigma union V star, and we don't put this restriction. So this is a restriction that the starting point is smaller than the ending point. Okay, which, by the way, that's always true. The starting is smaller than the ending. What about the empty word? Okay, I'm worried about that. Okay, but that's so if we leave out this restriction, we get such things, unrestricted grammars. The point is, we have finally come to the top of our thing. Chapter 3 and 4 deal only with this top line. This whole thing about context sensitive is mostly ignored by the book. It's mentioned, I think, once. It's mostly ignored. We're going to spend 10 minutes doing an example, and then we'll stop. But now, we finished our diagram. So let's draw our diagram that we've been drawing since the first day of class, and we'll have it down pat. We're going to spend the rest of the time dealing with things in the diagram, but finally, at last, we can see the entire diagram. So let's remember, you have an alphabet. That's finite. You have a set of words. That's countably infinite. You have the set of languages. That's great. Each dot here is a language. We spent the first month talking about regular languages. Not the first month, the first 2 weeks. Then for 3 weeks. Then we spent a lot of time talking about context-free languages, right? And the end of the class, we saw that there are certain things that are not context-free. Let's just remember them. A to the N, B to the N, C to the N. That's not context-free. Okay. Another thing we saw was A to the N, B to the M, C to the N, D to the M. Okay. That's not context-free. Okay. And I think there were a few others, whatever. But it's not important. Whoops, I'm not going to draw that point. I'm going to draw it over here. Okay. The point is, we have higher things. And the higher things, one of the higher things is context-sensitive languages. And we're going to spend one time doing that, and I'll tell you exactly the language we're going to do. We're going to find a context-sensitive language, which we saw. Oh, here's another thing. WW. Remember? In here we had WW reverse. Those are palindromes, or even palindromes. Okay, that's in here. That's a context-free. But WW without it, without the reverse, we said we can't do it in here. I didn't prove it, that you need the pumping lemma for context-free grammars, but I said that it's out here. Well, it turns out to be it's context-sensitive. We're going to do the example that does exactly this. Okay? In 2 minutes, we'll do the example that does exactly this. And that's it. That's all we're going to say about context-sensitive languages. Just for your curiosity, you might ask, what machines does each one of these correspond to? Okay? And the answer is, regular languages correspond to push-down automatons. Regular languages correspond to finite automatons. Context-free languages correspond to push-down automatons. Context-sensitive languages correspond to something called linear bounded automaton. We are not going to talk about them, but they're what I might call they're Turing machines with a restriction. Doesn't matter. Okay? And finally, there are certain things that can't be done by context-sensitive languages. I don't have any example offhand, but you can look it up. And then the highest thing that we're going to talk about is RE languages, recursively enumerable languages. We are going to talk about things over here. Okay? All of Chapter 3 is all about things in here. And in Chapter 4, we're going to talk about things that are in here and over there, outside of RE. Okay? At the end of Chapter 4, we're going to talk a lot about, well, we're going to give one major theorem about stuff that's out there. Okay, so that's a complete picture of what we have. This is the 4-level hierarchy: regular, context-free, context-sensitive, RE. Okay, and we'll spend that. Great. So, stop. Now, I want to do a half-hour musical interlude and write a grammar, a context-sensitive grammar, that does WW like that. Okay? And I don't need to waste your time while I'm writing it. Okay, so WW, we said we can't do this with a push-down automaton, because if you think about it, you put the word W on a stack, then when you pop it off, it's going to come in reverse. So it's very easy with a stack to do WW reverse. But how do you do WW? Well, by the way, there's no problem doing it with a computer. How do you do W with a regular computer? Let's say I give you a word as input, and I ask you, is it of the form WW? So what do? You go back and forth from the beginning till someplace. You have to do it non-deterministically because you're not sure where is the middle point. But you go and you try to look for the middle point. By the way, you could look for the middle point here. Go through the word, count how many letters there are, then go to the middle point and make sure this letter is the same as this letter. This letter is the same as that letter. This letter is the same as that letter. Keep on going till the end of the word. You got it. So it can be done with a regular computer, but it can't be done with a push-down automaton. Okay? But it can be done with this context-free grammar, and I'd like to show you how a context-sensitive grammar goes as follows. S goes to FM. F and M are two variables. What they're supposed to stand for is the beginning of the word, exactly like I said, the first and the middle. Right? You're standing with the first and the middle. And then what do you have to do? You have to make sure that the letter here is the same as the letter here. Then you have to go next and make sure that the letter here is the same as the next letter, and et cetera, et cetera. You keep on doing it. So this is the first place, this is the middle place. Okay? Then you're going to have two what's called messenger variables. Okay? A and B are messengers. They are messages from the first to the middle saying, hey, I saw an A. Make sure that there's an A on this side. Make sure there's an A on this side. Okay? I saw a B. Make sure there's a B on this side. So here's your messenger. Go across. Make sure there's a B on this side. Now, the way I described it is the way a computer will make sure that the word is of this form. But now I want to talk not of a computer, but of a grammar, and I want to talk about generating a certain word. Okay, so we're going to do it like this. Okay, so let me just go through generating. So S goes to FM. We're going to do an entire sequence, and it'll be nice. Okay, now if you have a first thing, then what you can do is you can generate either a small a or a small b. If you generate a small a, then make the a messenger. That's the messenger. If you generate a small b, then make the b messenger. In other words, these messengers are to go to the middle and tell him, hey, middle guy, I have an a, or hey, middle guy, I have a b. Okay, let me just show you how messengers work. By the way, till here is context sensitive. There's only one letter on this side. Okay, but look at this. It says as follows. If I have a capital A and I have a small a, swap them. The point is, these are messengers. They're going this way. So I want to leave the small a, but I want to keep my message going. If I have a B, swap them. Okay, these are context sensitive. We never had rules like this where we have two things on this side. Okay, same thing with the B messenger. Just swap them, keep on moving this way, forget about the terminals there. Now, finally, let's say I have a capital A, that's my messenger, and it hits the middle barrier, that's the middle letter. Okay, what do? Then leave, I want you to absorb the message, and on the other side, print an A. If you have a B hits the middle barrier, then I want you to absorb the message and put a B on the other side. At the end, I want to get rid of the F, I want to get rid of the M. Then I'm going to have an entire word. Let's start. So I want to generate the following word. Let's think of a nice word to generate. How about this? A, B, A. Okay, that's the first word. And then I want A, B, A. Okay, and we're gonna generate this word. This is W followed by W. Okay, and any word of this form can be generated like this. Okay, in the alphabet A, B. Okay, so let's start. It's going to be a long thing, and we're going to do some short thing. You're going to see it's not going to be so hard. S goes to FM. That's that rule. That's the last time we'll ever see that rule. Now, I want to generate an A, so I do as follows. Ready? This goes to FA, then the messenger A, then M. Great. Next, AM. When I see AM, what do? I do F. Now notice, I need the context. I need both A and M. I need to see that A is in the context. So I get FA, then M, then A. Okay? Finished. I now generated the A from this side of the word and from this side of the word. AA. Great. Let's go on. Next, what am I going to do next? I'm going to generate the next A. So it's going to be F. We'll change the F to another A. So it's going to be F. This F turns into F A, capital A, because that's what I'm doing. So this F turns into that. And don't forget you have an A, an M, and an A. Okay, great. Now this is my messenger. This is what I told you about a messenger. It's going to go and knock into the middle barrier. But before it knocks into the middle barrier, it's going to have to swap like this. A and A goes like this. So this becomes F, A, messenger, M, A. Okay, great. Now, when A hits the messenger, when the messenger hits the middle barrier, it produces an A on the other side of the barrier. We never go to the other side, but we do that. And so we get F, A, hits the barrier, it changes, it becomes M, A. So M, A, don't forget that A. So we have that. Notice we produce the first two letters of this side, we produce the first two letters of this side. Next, we're going to do now a B. So we're going to change this F to an F, B, capital B, two A's, middle barrier, two A's. Okay, now I'm going to be a little bit quick here, okay, but every time you see a B and an A, you swap it. So this basically goes till here. And so we're left with the following. This becomes F, B, A, capital B, M, A. Okay? Holy cow. I did it wrong. I did it wrong. Okay, fine. I'm not doing this word. I am doing, well, I'll show you in a second. I'm doing A, B, A, B, A. And you have to generate the words from the right to the left. Sorry. So this is W. Sorry. This is the problem of teaching a class without students in back of you to make fun of you, to make sure that you get it right. B hits the middle barrier and produces a B, and so this becomes F, B, A, M, B, A. That's what we're doing. And finally, we're going to produce the first letter of both, okay? And it goes as follows. F, A, capital A, send my messenger, B, A, middle, and then B, A. Okay, great. And now this A messenger is going to go all the way there, and we're going to get F, A, B, A, capital A, M, B, A. Okay, it's going to cross the barrier. A hits the barrier, the middle barrier. It crosses and produces an A. And so this becomes F, A, B, A, M, A, B, A. Okay, we have A, B, A. F goes to the empty word. EM goes to the empty word, and you're left with A, B, A, B, A. Nice? Very nice. Okay, that is an example of context-sensitive grammar, and it's very nice. But the book doesn't spend time on it, and I'm not going to spend time with it because we want to get to the more interesting part of the class. The more interesting part of the class is this highest level called RE, and basically the reason why it's the most interesting is because your personal computer can do that. So till now, we've been talking about these weaker versions of computers. Push-down automatons which have no memory, finite automatons which have no memory, push-down automatons which just have a stack, these types of machines, which I don't even want to talk about it, okay, these things. Now I want to talk about unrestricted grammars, recursively enumerable, and finally Turing machines. And it's going to be a theorem that says Turing machines can do whatever your computer can do, but more interesting, what your computer cannot do, a Turing machine cannot do. What a Turing machine cannot do, your machine cannot do. So now we're finished with the baby computers, the subset of this class which dealt with formal language theory, this subcomputer things, and now we're just talking about computability theory. Okay, give me a second. Okay, so let's start chapter 3 formally. So what we need, let's just talk about machines for a second. So we started off with finite automatons. Okay, finite automatons have different states, okay, and they read the input, okay, and they keep on reading the input, and they move to the right, and if they're accepted, and if not, not. We saw that that's not enough, and so we added in, I don't want to do this, I don't want to mess up your notes, we added in a stack. We saw that that's not enough, so we need something more, okay, and so what we get more is something called a Turing machine. This was invented by Alan Turing in the 30s because he wanted to describe what a computation is. We're going to get to that a little bit later. Okay? I just want to back up and motivate a little of his thinking. He asked himself the following question: what is a computation? And he said as follows: you know what? Alan Turing was a mathematician. He was a real superhero mathematician, and he said, I do computations. I do computations. So what does a mathematician do? He takes a piece of paper and he writes things on it. Sometimes he crosses out, sometimes he changes one thing into another thing, sometimes he checks what he wrote, sometimes he adds what he wrote, etc., etc. So he takes a piece of paper and he writes on it. So Alan Turing wanted a computer to do exactly that. Okay? What does a computer do? It reads and writes on a piece of paper. Great. Now ask yourself the following question. What size paper? Should it be an 8 by 10? Should it be a 10 by 12? Etc., etc. So Turing was very much influenced by two things. One is a typewriter ribbon. If you think about a typewriter ribbon, I don't know, boys and girls, there was something called a typewriter before word processors. Okay, a typewriter ribbon is something that goes on a typewriter, and basically it's a thin sheet that has ink on it, and you type and you hit it. But the main point is that thin sheet, you can type anything whatsoever into that thin sheet. Okay? When you're typing and the typewriter maker has no idea what you can do, you can type any string of letters whatsoever. Another thing that extremely influenced him, and you have to understand this is the 1930s, was a ticker tape. You know, you've heard the phrase ticker tape parade, but a ticker tape is, before they had on the bottom of your screen the listing of the stock prices, they used to have a piece of paper, and on the piece of paper they would write all the stocks and the prices for the stocks. And this was something that's that went across the city. Okay, just historically, a ticker tape parade was when you would go down Wall Street, and people who were working in Wall Street, they would have a parade, and they would want to send something out to show, you know, hey, we love that guy who just fought in that battle, whatever, the general or the president, whatever. So what they would do is they would open their window and they would take these ticker tape sheets of paper which had stock prices for weeks and weeks and weeks, and what else are you going to do with them but throw them out the window? And so that's where the phrase ticker tape parade comes from. But anyways, Turing was very influenced that one sheet of paper can have all the information possible. In other words, you don't have to have a paper this size by this size. You can just have one sheet of paper, and the sheet of paper can have boxes with information, and in each box can go one symbol. Okay, so he said as follows. Okay, this is Alan Turing. Okay, he said as follows. What is a computation? It's a machine with memory, not like a finite automaton, not with a stack memory, but more random access memory, in the sense that you can get from any place in the memory to any other place in the memory. I don't like this restriction where you can always look at the FIFO, LIFO, the last thing put in. You should be able to look anywhere in the memory. Okay. Now, Turing was extremely influential. Our computers are based somewhat on some of his ideas. His ideas and a guy named von Neumann who knew his work, etc., etc. So think about our memory. Think about the memory in your computer. What does that memory have? It has the input, it has the program, it has the output, it has everything jumbled together in one memory. You store things here, you store things there, different parts of the memory, etc., but it's in memory. Everything is part of the memory. The input, not the program, but the program is not here. Okay, the input and the memory is stored the same thing. Turing had this thing not only as a place to have memory in it, but also as a place for storing. Not only as a place where you can read your input, but also as a memory place. Now, one of the changes that you need is, in the finite automaton and in the pushdown automaton, you always started at the beginning input and moved here and moved here and moved here. Some things you put on, sometimes you put things on a stack, sometimes you didn't, and moved here and moved here. But now we need random access memory. We need to be able to go backwards and forwards. We need to be able to go here and here. So that's one change that we have. We need to be able to go backwards and forwards, not just keep on moving to the right. And the second change is, in a finite automaton and in a pushdown automaton, all we did here was read. We read the input. Now, I not only want to be able to read the input, I also want to be able to cross out some symbols and write to this tape also. Okay, now we're going to do examples of Turing machines. I'm going to do several examples of Turing machines, but what I want to do is I want to give you the formal definition first, okay, and then we'll go through some different things. But keep this picture in mind. This is a Turing machine is a machine. It's going to have a state just like before. It's going to go backwards and forwards. It's going to be able to go backwards and forwards, and it's not only going to be able to read, it's also going to be able to write. Okay, just one historical thing. Okay, till now I said a lot of the stuff we were doing was done by Chomsky. Okay, not all of it, but some of it, a lot of it was done by Chomsky. But now we're going back. Chomsky did his work in the 50s and the 60s. Okay, but now we're going back to the 30s, and Turing came up with this idea of a Turing machine. Somehow all the ideas are a little bit mixed up with what machines and finite automatons and grammars. I'm not a historian. I don't want to be a historian. There are history books that deal with this, but I was just making it more intuitive. Okay, but anyways, we're going backwards. This whole field of theoretical computer science was done by many different people in many different countries at many different times, dealing with many different issues. But somehow or other, they come together to do the work. Okay, so just like I gave you a formal definition of a finite automaton and a formal definition of a pushdown automaton, I now want to give you a formal definition of a Turing machine. Okay, so definition. A Turing machine is a 7-tuple which consists of, okay, so we can write it out, okay. Some of these things we've seen before. We know some of these things, and again, we're just building our previous ideas. Okay, Q, a finite set of states. Just like before. Okay, sigma, an input alphabet. Okay, again, we are going to put words on the machine, and we're going to ask, is this word accepted, or is this word not accepted? We can also do other things, but in the beginning, this is what we're going to do. Gamma, we saw this before. Before this was the tape alphabet, was the stack alphabet. Now we're going to make it, we don't have a stack anymore, we're going to have a memory. But if you think about it, you know what? In your computer, you can generate a stack. You learned how to generate stacks and deal with stacks. So too, why? Because you have random access memory. So too, we're going to be able to deal with stacks in our random access memory in our Turing machine. But we're not going to call it a tape alphabet. We're going to call it, we're not going to call it a stack alphabet. We're going to call it a tape alphabet. These are the symbols that can go on the tape. Okay. Now, the input goes on the tape. This is all the symbols that goes on the tape. So we have the following. Okay, comma. The input alphabet is a subset of the tape alphabet. What we can put in as input will be allowed to be put on the tape. Okay. Guess what? Our transition function. This is the most important thing. This is the most important thing, as always. Okay. I just want to finish off the list, then we're going to talk about the transition function. It's always the hardest one, but we'll do it. Okay, let's just finish off the list. QS is a starting state. Q accept. So this is a member of Q. This is a member of Q. This is an accepting state. We only have one accepting state. Beforehand, some of our states I double circled. We could have more than one, but here we only have one. And we also have Q reject. Okay, we have one rejecting state. It's also a member of Q, and it's called the rejecting state. So I have to talk about the transition function. So I am going to talk about the transition function, but I want to remind you what we saw before. So take this, I'm going to erase it. So let's remember the first day of class. We talked about finite automatons. Okay. And we said a finite automaton, the transition state is as follows. Transition function is as follows. You give me a state, you give me an alphabet, and I will give you a state that you can go into. Great. Okay. Okay. I just want to talk about deterministic. Let's talk about deterministic push-down automaton. So this is a deterministic finite automaton. Push-down automaton. So what does that say? That says, just like before, you give me a state, you give me a symbol that you're reading, but also tell me what's on top of the stack. Tell me what's on top of the stack. And I will tell you two things. One, what state to go into, and also what to push on the stack. So we saw that before. Now we're going to do deterministic Turing machine. You don't have to worry about the word deterministic now. We will talk about non-determinism later on. Okay? And it goes as follows. Just like before. Tell me what state you're in. Because this is what a mathematician is. Sometimes he's in this state, sometimes he's in that state. He changes different states. Okay. Tell me what symbol you're looking at. What symbol are you looking at? This is like this. What's the thing you're reading? The next letter you're reading? Well, you could be reading anything on the tape. Not only symbols that you put on the tape. I'm sorry. Not only input symbols, but symbols that you put things on the tape. Okay. And I'll tell you what state to go into. Also, I'll tell you what symbol to write there. This is a new thing. Because the input tape, we can change things also. If you want, you can leave things alone, but you can, at every point, you can not only read what's in there, but you can write a letter in there. Okay? And then tell me. This is something else we saw which is different. You can go to the left or you can go to the right. In both of these, after reading a letter, you're always moving one to the right, one to the right, one to the right. Here you can go either to the left or to the right. This is what random access is all about. Okay? Great. So this is what your transition function will be. Let's just go through it again. Tell me what state you're in. Tell me what you're looking on. I'll tell you what state to go into, what to change the symbol, or what symbol to put where it was, and then how should your little eye move? Should it move to the left or to the right? Okay, I just want to do some notation that we did here, and it goes as follows. Okay, I want to do 3 levels of notation. Here, you're in state Q35. You see the letter A. You see the letter A, and you go to state Q72. Here, we needed to put in other things. So let's do this. You're in state Q35. You go to state Q72 like before, but now you have to also look, not only are you looking what you saw, but you also have to look what you popped off your stack. So we had comma B, and then what you put onto your stack. We had comma C. So remember, what you read, what you pop, what you push. Great. Now let's do this. Again, you're going to have state Q35. You're going to have state Q72. Okay? And here you're going to have A. That's telling me what you're reading on the tape. And then, what should you do? Okay, this tells you what state to go into, that's that. But what should you do? You should write the letter B if you want, and then you should go to the left. Okay? You could also have Q, let's just change the numbers for the hell of it, 61. You can have X. Okay? Take the X, make it into T, okay, and then move to the right and go to state Q95. Okay, so these two examples are typical moves of your Turing machine. Okay, that is very nice. Okay. Okay, great. Now, okay, so let's do an example of a Turing machine. Now that we saw it, let's do an example of a Turing machine. I'm going to do it in two different ways. I'll show you. Give me a second. Okay, I just want to tell you, Turing machines are a pain in the neck to program. They're horrifyingly complicated things to program. And the reason is as follows. Because you have to really you're dealing with just one string of memory. So you have to be able to go back there and back and forth. So if you program, you know programming is hard. If you program in assembler, or if you've ever seen programming, you know you have to get into the really details of assembler. It's much more painful. This is 100 times more painful than assembler. Okay, so this is a little bit painful, and I'll explain to you how we're going to get rid of this in a second. Okay, so I just want to show you a problem that we're going to do. The problem is as follows. Little addition. Okay, now, first thing, what are we adding? Well, usually you add numbers. We already have a problem, okay? Because how do you add numbers? It's a little bit more complicated, okay? Well, computers don't really deal with numbers unless we put in all the digits on, which we can, but I don't want to deal with that. A lot of times, assembly, it deals with binary numbers, zeros and ones, because electricity goes through the circuit or electricity doesn't go through the circuit. Here, binary, and you have trouble, people have trouble learning even binary. Here, we're not going to do binary, we're going to do monary, okay? So, 1, 2, 3, 4, 5, that's going to correspond to the number 5, okay? 1, 2, 3, that's going to correspond to the number 3. Okay? Okay, great. Now, let's talk about addition. What has to be the input? You have to input two numbers. So let's say I wanted to add 5 plus 3. So what I have to do is, on this piece of paper, I would put in 1, 2, 3, 4, 5. Then I have to somehow separate my input. So this is monary. We don't use ones and zeros, just ones. This is the oldest numbering system in the world. So I use a B for blank, and then 1, 2, 3. Okay, great. Okay, the rest of the tape will be blanks. B for blanks. An infinite amount of blanks. Okay, question. How should we add this? So what we're going to do is as follows. By the way, what's 5 plus 3? It's 8. Okay, so what we're going to do here is as follows. We want to add 5 plus 3. Here's what we can do. We're going to cross all these ones. We're going to look at this one, we're going to look at all of this one, we're going to look at this one, we're going to look at this one, we're going to come to here. What do we want to give at the end? We want to change 5 plus 3 into 8. Okay? We separated the inputs into two different parts, which is what we wanted. But here's what we should do. We should change this. I'm going to change it like this. We should change this B, the blank space, into a 1. Okay, but one second. We have a problem here. Because look how many ones we have here is the final answer. 1, 2, 3, 4, 5, 6, 7, 8, 9. 5 plus 3 is 8, not 9. Okay, so what we have to do further is go to the end till we get to a blank, back up, and change this 1 into a blank. Now let's go through it. 1, 2, 3, 4, 5, 6, 7, 8. That's exactly what we want. That's the final answer that we want. Okay, but now we have to describe how to do that. I'm going to describe it in two different ways. One is like this. I'm going to tell you what state we're in, what we see, what we write, what state to go into, and which way to move. Okay? So this gives you all the information of those rules that we have. So watch what it does, and then we'll go through it and we'll do it again. So you start in QS. You start. Okay? If you see a 1, you write a 1. In some sense, you can think of this as halfway. This is what you see, this is what you do. Okay? You write a 1, you stay in QS, okay, and you move to the right. Let's just see what that says. You start here, you see a 1, you write the 1. That means you don't change anything. You move to the right. This is a loop. You see a 1, you leave the 1, write the 1, move to the right. Stay in the same state, move to the right, etc., etc. Keep on doing that. Now, at some point, you're going to come to QS, and you're not going to see a 1, but you're going to see a blank. Well, what should you do? Well, you should change the blank into a 1, and then you should go into QE. E is for erase. Change it and erase. Move to the right. Okay, we're now in a new state. We were in Q start, now we're in Q erase. Go to the end and erase. Okay, great. So let's do this. Q erase. You see a 1. Change the 1 into a 1, which means cross over all these 1s. Stay in Q erase. Keep on going to the right. Okay. When will you stop? Well, when I am in state Q erase, I see a blank. That's this blank. Not this blank. I changed that blank. That's this blank. That's the first blank afterwards. Leave the blank. Don't want to change this blank. I want to leave that blank. Go to QB, B for back up. Back up a little. And then go to the left. Okay? And finally, QB. You're going to see a 1. That's this 1. Change that 1 to a blank. Go to Q accept. And I don't care afterwards if you go to the left or to the right. You might as well go to the left. Okay? At the end, you will go till the blank. You'll realize, oh, I came to the end. Back up. Change the 1 into a B. And accept. Okay, I'd like to show you how to do this for another one. Now I just have to say, this is for 5/3, but this program will work for any x number of 1s. Okay, and blank, any x, y number of 1s, and it will result, the result will be x plus y number of 1s. Okay, so that's a program for any input whatsoever. Okay, I'd like to write the same program. You have this, but I'd like to write the same program in the notation of the book, and then the notation that I showed. Basically, it's as follows. You start at QS, and while you're in QS, you have the following. Let's do this. If you see a 1, then what should you do? You should leave the 1 and go to the right. Okay. Eventually, you're going to be in QS, you're going to see a B. That means the middle barrier, that's your middle barrier B. Okay? And what you want to do is, you want to change that middle barrier to a 1 and keep on going to the right. Then, you're going to be in Q erase. That means go to the end of the word and erase the last 1. And so you have the following. While you're in state Q1, QE, if you see a 1, move to the right, leave the 1, and go. This means cross the X input. This means cross the Y input. Okay. Eventually, you're going to come to the end of all the Y's. So what do? You're going to come to a B. What should you do with that B? Leave that B and go to the left. Okay. Okay, great. This is state Q backup. Q backup. Okay, need a little bit of room, so we're going to go down here. Okay, you're now in Q backup. If you see a 1, you will see a 1 because you just crossed a bunch of 1s. You will see a 1. Change that 1 to the blank. This and this is the same thing. I mean, not the same thing, but these two are. This just says cross the first thing. This is cross the second input. This changes the 1 to a blank. Okay, and then when you finish that, you go to Q accept. If you want, you can doubly circle that. Okay, you are accepted, you are finished. Okay, great. I'd like to show you another one, which the book does. The book does on page 173. Okay, and it's this, W number W. Now we did this with a grammar. Okay, so we did this with a grammar, but I want to do it here. Okay, I just want to say this thing that I just accepted, this thing that I just erased, has the following thing. Till now, we've always been doing the following. We input a word and we see if the word is accepted or not. But this thing that I just erased, it did something else. It did a computation. I plugged in X, I plugged in Y, it gave me X plus Y. That's different than a finite automaton and is different than a pushdown automaton. It's what a regular computer does. So we're going to have two different things that a regular computer can do. One, determine if a word is in a language. Two, do a computation. And we're going to be doing both. Okay? Okay, so now I want to do this. We did something like this with a context-sensitive grammar, but I want to do it with those rules that I showed. And the reason why I want to do it is as follows. I want you to see the difference between the grammar and this. Now it's a little bit different if you have easier if you have the number sign, so at least you know how far to go. If you remember from the grammar, what I said was count how many things to do and then go halfway through. That's a little bit hard to do with a Turing machine. Counting, dividing by 2, a little bit hard. So we're looking for words like this, and you'll see how to do it. The rules are like this. It's not in the book. Okay, something similar is in the book, but I'm doing my own version. You don't have to waste time writing it. I will write. Okay, so this is what we're doing. The alphabet, I didn't even finish, but the alphabet is as follows. The alphabet is 0, 1. Okay, and what you're going to do is, let's say you see a thing, something like this, 0, 0, 0, I'm sorry, 0, 0, 1, 1, 0, 1, number sign, 0, 0, 1, 1, 0, 1. Okay? So you put, this is put on the input. And you want a program, that's a program, this is a Turing machine that's going to do this. Here's what you're going to do. You're going to see a 0 here. You're going to go into state Q0. Okay? You're going to cross it out. Okay, we'll go through it like this. We'll do it in a second. Then you're going to cross across these things. You're going to cross the whole first word. This is just like the messengers crossing over. Okay, you're going to come to the middle barrier. Here it's a number sign. Okay, great. Then you're going to see a 0. Okay, you just look. You had a 0. You're supposed to see a 0. Great. You cross that out, and then you go back. Okay, great. Now let's see what happens next. Now you go back to the number sign, you reverse till there, then you go reverse here. Then you go all the way till here, and you say, oh, I went too far. And then what you do is, you come to here, and you start all over. Okay, so let's start all over. You see a 0? That's great. You go here, keep on looking, look for the number sign. The minute you find the number sign, now you say, okay, great, I'm still looking for a 0. Now I cross this x. We didn't have this x before, but I cross this x. Now I see a 0. Cross it out. Okay? Back and forth, back and forth. You're going to go back. You're going to reverse past all the x's, reverse past the number sign, reverse past this, come to a second number sign. Guess what? You're going to see a 1. You now go into state Q1 and you say, okay, I just saw a 1. Cross it out. Make sure there's a 1 on the other side of the barrier. So you're going to cross over the barrier, cross over the x's. The first thing you should see after that is a 1. You do, you keep on going back and forth, back and forth. Okay, let's just go through the thing. This is, again, worse than programming, but it's doable. This is the start state. You either choose, what do you see, a 0 or 1? If you see a 0, cross it out, stay in state Q0, go to the right. If you see a 1, if you're in Q start, you see a 1, go to state Q1, which means I just saw a 1, cross it out and go to the right. Okay? I'm going to go forward and do this. Okay, this whole thing is Q0. What does it say? It says, you see a 0, you're in state Q0, you want to cross the first series. You're a 0, you stay in state Q0, leave the 0. You're a messenger, just leave it, keep on going to the right. You see a 1, keep on going, cross. You're going to see a barrier, cross it, but now you're on this side of the barrier, so we're going to call it Q0 prime. Leave the middle barrier, you don't change the little barrier, keep on going to the right. You're in Q0 prime, you're on this side of it. You see an X, what do? Stay in Q0 prime. Leave the X alone. The X is these beginnings. Okay, on the right hand side, you want to cross it. Finally, you're in Q0 prime, you see a 0. You were looking for a 0. This is the main thing. The main thing is, do you have a 0 on that side of the middle barrier? Yes, take that 0, cross it out, go into Q reverse. Okay, start moving back to the left. Go to the beginning of the word. Okay, now this is all Q0. This is all if you see a 0 here. If you see a 1, you go into state Q1. This is the same thing. Look what it says. It says fast forward till the number sign. Fast forward till the number sign. So you're in state Q1. You're looking for a 1. You keep on going, keep on going. Here you change the 1 into a blank. It's the same thing as here. You're going to have to look at it yourself. Okay, now reverse. Let's just look at what reverse is all about. Reverse means cross all the x's this way. Notice all lefts. Cross the middle barrier. Cross the middle barrier. This way. Cross the words. Cross the letters that you saw here. Great. Finally, Q reverse prime. You see an X. That means you've gone too far. You've gone till here. Go to the right. Leave the X alone. Don't change the X. Go to QS. Finished. You're done. Okay? This works it. Now, there's other things also, because you want to make sure that when you go back and forth, you have to check that there's nothing afterwards. So you have to make sure that there's a barrier. I'm going to leave it alone. It's not that interesting, but it's just to show you the complexity of programming with a Turing machine. I'd like to show you the same program, but in the book's notation. So it looks a little bit simpler like that. I like it, okay? But here you can see the loop. Because there's a loop, you're going backwards and forwards, so you can see the loop a little bit more clearly. But I did the old-fashioned notation, 5 tuples, because I wanted you to see how complicated and how ugly it is. But it's good. Okay, here it is, QS, you're in S. There's 2 possible things you can see. Okay, one possible thing is you're going to see a 0, and what you're going to do is you're going to cross that 0 out, go to the right, and now you're in Q0 because you're looking for 0. The other possibility is you're going to see a 1, you're going to cross it out, and you're going to keep on going to the right. And you'll be in state Q1, which means go find me a 1 on that side of the barrier. Okay, now here you're going to have 2 things. I'm going to see a 0, you're on the left side of the barrier, and you're going to see a 0, you're going to leave the 0 and go to the right. You can see a 1, you're going to leave the 1 and go to the right. That makes sense. You're not changing anything in the first part. Okay? Same thing over here. you're going to see a 0, you're going to leave the 0, go to the right. You're going to see a 1, you're going to leave the 1 and go to the right. Great. But eventually, in both cases, you're going to see the middle barrier. There. You're going to see the middle barrier. Okay? And what you do with the middle barrier is leave the middle barrier alone and go to the right. Okay? Leave the middle barrier alone and go to the right. Okay? Now, you're in state Q0 prime. You're still searching for that 0, but now you're on the left side. I'm sorry, the right side. Now you're in state Q1 prime. See, there's a certain symmetry here. Okay, there's something else that can happen here, and I'll talk about it in a second. Okay, now, what are you going to see on this side? Well, what you're going to see on this side is the x's that you crossed out. So x, you leave the x alone, and go to the right. Same thing here. You're going to see an x, you're going to leave the x, you're going to go to the right. Eventually, you're searching for a 0 prime. If you're searching for a 0, that's this thing. If you find the 0, you're going to cross it out and start going to the left. If you're down here and searching for a 1, you're going to cross it out and go to the left. Eventually, then you get to Q reverse. Okay? And now here's where I run out of steam. Okay? Because you're going to go reverse. I'm not filling this in. You're going to go Q reverse prime. You're going to reverse the right side. You're going to reverse the right side. Okay? You might have a few other states, and then you're going to start over again. Okay? So this starts on the left side. You move past the middle barrier. You cross out those things. You start all over and go like that. Now, just another thing that you could do is, when you're in Q start, you could see the number sign, which means, let's just do that, the word that we saw before. Well, let's do it in a smaller word. 001, number sign, 001. Let's see what's going to happen. I cross out this, go across, cross this out. Cross out this, go across, cross out this out. Cross out the 1, cross the middle barrier, see the 1, cross this side. Now I go back. I see the X. I go to Q start here. Change in here. Now I Q start and I'm here. Now what that means is I finished the word. Okay, but there's something else that could happen. I could have a 0 here. So I better make sure that there's no 0, because this word is not accepted. So I'm going to call this, if you see that, so then leave the number, go to the right, and go to Q check. Okay? Q check makes sure that the number, the thing after all the x's, is a blank, so that you don't have that case. Okay? And if the check is right, if the symbol after the 1 is a blank, then I go into Q accept. Too many nitty-gritty details to get into it. I don't want to spend too much time on it, but that is exactly what we do. Okay, great. Let me just go through some of the examples that the book does. Again, my goal in life is to get you to read the book. So the book does, anyways, that's very pretty, by the way. You can see the loop, and you see the two possibilities that you can have. Okay, the book has nice, pretty pictures also. Okay, the book has O, that's the symbol 0. How many symbol zeros? 2n. 2 to the n. Okay? And the way, so this is on page 143. And the book also has A to the I, B to the J, C to the K, such that I times J equals K. So that's very interesting, because we showed with finite automatons you can do addition. We also showed with pushdown automatons you can do addition. But with Turing machines, you can do multiplication. So that shows already a certain power that this has. Okay, it's a very nice thing. Let me show you another thing that the book does. The book does the following language. number sign x1, number sign x2, number sign xl, such that xi, all of them are members of 0, 1 star. They're all words in 0, 1. But we have the following thing. xi is not equal to xj for I not equal to j. Okay? They're not equal. Okay, I'd like to, now you're reading the book, and you have to look at the book's examples. You don't only have to look at my examples, you have to look at the book's examples. I just want to show you how this is done. The way this is done is it starts over here. Okay? It looks at x1. It then goes through, traveling through, make sure that all the other ones are not equal to x1. Then it backs up, looks at x2, make sure that all those are not the same as x2. Backs up, etc., etc. Keeps on doing it, keeps on doing, keeps on doing, keeps on doing until it comes to a blank. Okay? Make sure that the xi is not equal to any of the ones afterwards. Okay? And the way it does it is very nice, worthy of doing, etc., etc. Okay, great. I just want to leave you with a little bit of homework for this section. No, I'm sorry, we're still in the middle of the section. We're going to do more homework problems, but I'd like you to write out real Turing machines for the following things. I wrote this in the homework sheet, but I want you to actually do it. So I want you to write this, a program that does this. F of x is equal to x plus 5. Okay, let me just tell you how to do it. Your input is a bunch of ones. Go to the end of the ones, add 1, add 1, add 1, add 1, add 1, get 5. Okay? So that's not hard. Another thing to do is f of x comma y equals x minus y. Assume x is more than y. Okay, so we did addition. I want you to show subtraction. And the way you do it is as follows. Okay, I'm not going to go through this on the videos, but you're going to have to do this. Let's say I give you 1, 1, 1, 1, 1, 1, 1, blank, 1, 1, 1, 1, blank, blank, blank. Okay, here's what I want you to do. Here's what I want you to do. You ready? Let's assume that's the way the data is given. Okay? Here's what I want you to do. I want you to go across like this. Start here. Okay? Now, you want to keep that there should be only one blank in the middle, and you'll understand why in a second. What you want to do is cross here, go to the middle barrier, cross here, go here. Then, what you want to do is erase this. You just change that 1 into a blank. Okay? Then, cross here, change that 1 to a blank. Okay? In other words, this is x, this is y. I just took off 1 from here, I want to take off 1 from there. Then you're going to go back again here, you're going to erase this, erase this, erase this, erase this, erase this, erase this. You're going to go to the middle barrier, you're going to look for another thing, you're going to stop right there. You're going to see left over 3. Okay, so that's x minus y. Okay, that's a lot of backwards and forwards. A lot of backwards and forwards. And finally, the last one I want you to do the following. F of x is equal to 2x. Okay, let me show you how to do that. Basically, you do as follows. Okay, here's what you do. Take this 1, put a 1 over there, put a dot on top of it. Okay, you make a new symbol with a 1 on top of it. Okay, go over here, go to the middle barrier, go 1 over, change this blank to a 1. Then you're going to go back. You're going to go till the 1 over here. You're going to change it back to a regular 1. You're going to go to the next one, put a 1 over there. Now, what you're going to do is, you want to copy that. So you're going to go, cross the middle barrier, cross the 1, come to another B, change the B into a 1. Go back. Erase that. You're not going to copy that one anymore. Now you're going to copy that one. Go back and forth, back and forth, back and forth. Eventually, you're going to have 1, 2, 3, 4, 5, 6. You're going to have 1, 2, 3, 4, 5, 6. A blank. 1, 2, 3, 4, 5, 6. Whoa! That's not your answer. Then you have to go erase this, make this into a 1, make that into a blank. Erase one more. Okay? And then you should have 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I'm wrong. Okay, I counted wrong somewhere, but that's what I want you to do. Okay, so that's your homework problem. It's in the homework things, but I want you to write a real low description of this. For each one, I want you to give me, you can make a diagram out of it. That would be very helpful, but it's important that you know how to do it. You will have to write a Turing machine in class. Okay, I think we've had enough for today. We'll do some more next time.